One of the things that I want to talk about is the amount of change that's going on in the industry. But it's not just change in the industry. Microsoft, in an important way, is in the process of reinventing itself. In a sense, you could say that Microsoft is inventing itself for the third time. The first time, of course, was when the company was created. It's a little hard to remember, or maybe even to believe in some ways, that Microsoft has existed since 1975. And to keep the three generations fairly simple, I've rounded things to decades and picked years that begin with 5. From 1975 to 1985, Microsoft as a company was focused on building the best interpreters and compilers in the world for microcomputers. It was a startup company focused on all the things that any company focuses on when it's just getting started up, getting basic systems in place, figuring out what the mission really was, figuring out how to ship products in volume, and being there at the creation of the microcomputer industry and figuring out what that was all about as well. It's probably a little bit hard to remember or even believe this today, but during that startup period, there was a lot of doubt as to whether a software company could even grow and be profitable. After all, it's not that many years before the creation of Microsoft, 1969 and 1970 in fact, that the software industry as a whole was created in the first place. And it was only a couple of years after Microsoft was created that the first software company ever went public. So many analysts were convinced that not only was the concept of a software product company a little bit of a risky proposition, but that even if software products were possible in mainframes and mini-computers, everybody knew that you couldn't build a large company around software for microcomputers. So those were the things we were struggling with during our first 10 years. During the next 10 years, we had shifted our focus from just building development tools to focusing on the platform broadly. One of the new things that we did in defining the platform, and again, it was a first for the industry, is we defined the concept of a platform and we defined the concept of development tools and broadened both of those concepts to include ordinary human beings working in their homes and in their offices. And so it was no longer just tools, as in development tools, it was also tools as in Word, Excel, PowerPoint, and so on, that were used for a different form of development. Our primary focus during that second decade was making our products complete, adding features, making them as powerful as possible. And of course, anybody who uses our products today will recognize that we were very successful in adding lots and lots of features to our products, almost to the point, in fact, maybe even beyond the point, where in many cases they've become so complex that nobody really knows how to use all of any of the products. Now, believe me, for every feature in there, there's some community of users who's passionate about it, but creating this powerful and complete platform has helped to frame the next challenge for us. My claim is a simple one. Computers will change more in the next 10 years than they have in the preceding 50. And I'd like to take you through a little bit of what that means before I talk about the approach we're taking to building the next generation platform. So, back in the 60s, when IBM introduced the System 360, the first modern mainframe, and along the way invented the concept of a family of computers that varied in size and power but had a constant instruction set, they also built one of the first large-scale modern operating systems, OS 360. And after having led the effort to build OS 360, Fred Brooks wrote a book called The Mythical Man Month. Now, how many people in the audience have read The Mythical Man Month? Okay, that means a lot of you haven't. And if I convince you of nothing else but to go out and get a copy of The Mythical Man Month, which is still in print, it's a very easy book to read, it's fun and kind of funny, if I do nothing else but convince you to do that, I'll feel pretty good. One of the things that Fred did in that book, besides inventing the term Man Month, is he talked about the 3 stages that a product went through, most products go through in the process of getting to the point where they're really fun to use. And what he talked about is that in stage 1, typically what ends up happening is that you build a prototype version of a product and it gets everybody excited. But it's too simple to really be used in any practical sense. Then what happens is you become convinced that this is a great product idea, and so you build the second version of the product and you start adding features to it. And you're trying to be complete. You're trying to make sure you don't leave out any feature that anybody might want. And you end up with what he called a V2 product, which is powerful but complicated. Now, the other thing that I've added to this chart is what happens in terms of commoditization of products, particularly in our industry, but it's true in other industries as well, is that in V1 we see prototype products that are built in very small quantities. In V2 we see products, for instance, in our industry, most databases are still in this category, sold in the thousands, very expensive, complex, and hard to use, and they require what we call SEs, what I liken to a personal mechanic, to keep them running. TP monitors fall into the same category today. And then what happens, Fred Brooks observed, most products never make it to this third stage, is we go back and rebuild the product. We keep the power. We keep the most important features, which is usually an amazingly long list of features, but we figure out how to build back in the simplicity. And because of that, we're also able to build the product in much higher volume, and then it becomes amazingly cheap. And in fact, if you look at, say, the personal electronics industry, you see this going on. You see things like tape recorders, first built as expensive prototypes and only used in recording studios. Then you see reel-to-reel tape recorders. And then you see eventually the introduction of things like Walkman, where you can carry the thing around on your hip. It's amazingly cheap. Nobody ever thinks about maintenance. In fact, you replace it when it eventually breaks, which it never does. And it's produced in the millions. And the main keyword that I finally came up with to describe the concept of something that's amazingly powerful but still simple, the word that I came up with is useful. Because I couldn't think of another word, and it just seemed like such an evocative word. So what I did is I put together a little table for some of the technologies that we find in the software world. For instance, development languages, which in the 60s were being invented. They weren't very complete. They were either not available or frightfully expensive. And then in the late 60s and early 70s, when I started to program, we saw the industrial stage. Lots of features, complex languages like PL1 were invented in that period of time. But boy, development was a complex and difficult activity. There was no such thing as a visual debugger. All the tools that we take for granted today are partially a consequence of the fact that languages became commodity products in the late 80s and early 90s. One of the most interesting testaments to the power of commoditization is that even the people building complex industrial software still in many cases tend to prefer to do their development on the PC platform and then port their actual code to Unix or MVS because the development tools in the commodity world are so powerful, so useful. So powerful and simple at the same time, so useful. Word processing. I had a Wang word processor in the early 80s. You could not buy a Wang word processor in those days without signing up for training. When you bought a Wang word processor, of course you had a maintenance contract, and you had a personal mechanic who came to your house whenever the machine broke. When I compare the power of that Wang word processor, which at the time I thought was a dream machine, to the features that my kids take for granted in Microsoft Word today, it is beyond amazing how Microsoft Word is simultaneously far more powerful and yet far more simple. In a word, useful. So I could go through the rest of this chart. The basic concept is simple. As we get towards the bottom of the chart, we find database, which even today in the late 90s is still mostly an industrial technology. Whether you buy SQL Server or Oracle or DB2, you tend to be buying a large, complex, expensive product which you normally don't think of a consumer installing himself. One of the key breakthroughs in SQL Server 7, which we expect to ship in a matter of weeks, is that it is the first industrial-strength database that was built to be self-installing, self-managing, little things like, say that you installed the database in Win98 and you didn't know in advance exactly how big your database was going to be. Every industrial-strength database in the world today, including SQL Server 6.5, the shipping product of ours, says that if you decided your database was 50 megabytes and you made a mistake, it's either 100 megabytes and you're out of space, or it's only 10 megabytes and you want to get some space back, you have to do a dump, and then you have to do a reload and a restore. How many end users even know what a reload or a restore is? And so we are seeing today the commoditization of databases and the commoditization of OLTP. When you get onto the internet and connect to Amazon and buy a book, ordering that book in a single click, that is the commoditization of online transaction processing. And we will see sometime towards the end of the zeros the commoditization of distributed technology. What we're seeing now is the movement of distributed from the prototype stage, where only a few large companies like airlines and credit authorization companies can build distributed systems, to the point where any large organization with a professional development shop can build those same distributed systems. And the point that I'm trying to make is that it is commoditization that is really driving the unbelievable change ahead of us. So when I think about Microsoft V3, I think about three things. The first thing I think about is distributed computing. One of Microsoft's challenges in V3 is to make it possible for you to build distributed applications, distributed from the server to the client, distributed from server to server, and distributed in large networks with millions of clients and hundreds of thousands of servers. The second thing I think about is that Microsoft's need to strictly search for completeness. For example, to think about, we don't have record locking, we have to put it in. We don't have a word processor, we have to build one. That search in many ways is behind us, and our next search is to begin to push the boundaries of the technology. Why can't we make it simple to build distributed applications? Why can't we make a database self-installing, self-maintaining, self-running, something that anybody would love to use? But most of all, ahead of everything else, I think that our challenge is to make computers useful. Now, to me, making computers useful has two meanings. The first meaning of making computers useful is that when you think about installing a new application on your computer at home or adding a new piece of hardware to your home configuration, you shouldn't have to wait for a long weekend before you start out on that journey. So when we get to the point that computers are as simple and easy to use as appliances, when servers run themselves and solve their problems most of the time without help from operators, we will have done half of the job of making computers useful. Today, if you go to a gas station, if you go to a restaurant, if you go to a small retail store or a medical clinic, the chances are that you will not find a server in that location. In the U.S. alone, there are 14 million locations to which a full-time worker reports every working day. There are a lot more home offices people don't work at every day. These are just the locations to which at least one full-time employee reports every working day. I claim that by the end of this 10-year period of time, every one of those locations in the U.S. will have a server. Many will have 10 servers or 100, but each of them will have at least one. And multiply that number by at least 3 to get the rest of the first world. And then because I believe commodity servers will penetrate the second and third worlds as well, multiply the number by 7 or 8, and you get tens of millions, maybe even hundreds of millions of servers. And the change that we see, the shift towards pictures, the shift towards digital originals, affects the corporate environment at least as much as it does the personal environment. Which means that today's world, where we have files and databases, and things like pictures live in files and things like numbers live in databases, has to shift to a world where all of the storage becomes integrated. The applications need to shift beyond manufacturing and basic decision support to things like Salesforce automation, which empower mobile workers, and the concept of web locations, the very type of application that makes self-service possible. The hardware will shift as well in the ways that I've already talked about. Now let's suppose that you work at home, or you maybe use a computer at home, and you get used to the fact that you can make an airline reservation with Expedia, you can buy a book through Amazon, you can order a computer from Dell or Gateway, and you can do all of that self-service. You can do it 7 days a week, 24 hours around the clock. You get more flexibility in the service, you get better help in terms of being able to ask questions, you get to automatically configure your machine. Not only can you place the initial order, but let's say we get to the point where you can check status and make changes online. How long will it be before you expect to see the same thing happening at work? And so I believe that the concept of EDI is going to be a critical concept in the next few years. So when I think about that inflection point, I think about 2 examples. I think about the consumer today picking up his telephone, talking to an intermediary at the other end who talks to a terminal, who talks to a server. It could be a mainframe, it could be a mini computer, it could be a real server, and that's how people place their orders today in the non-self-service world. I also think about manufacturing companies, to take one example, with their ERP server, and when they run low in inventory, somebody reads a report or gets a message on the screen, that's an intermediary, picks up the telephone, talks to an intermediary at the other end, who uses a terminal to place an order against the computer at the other end. And I see all of this shifting. The consumer, even today, uses his computer, which has a terminal inside it. Perhaps it's a bit hard to see the graphic, but what I'm showing is a workstation running a browser. So that's a computer with a terminal inside it, talking to the server. Now, the other thing that I see happening is servers talking to servers. Why, when the ERP system notices that the company is low on inventory, why can't it just order inventory completely automatically? The thing that really happens on this slide is that the intermediaries disappear. An entire class of terminal-bound, single-function, single-tasking workers disappear over the next 10 years. Now, does this mean that, for example, banks, because they no longer have somebody on the phone, no longer have somebody at a teller station who just moves money from one account to another, does this mean that banks no longer have employees that deal with customers? Of course not. What it means is that increasingly the employees who do service functions within an organization shift from being single-tasking intermediaries to being true advisors. Somebody who can give you good advice on your investment portfolio. Somebody who can really talk to you knowledgeably about what your network ought to look like, and so on. Finally, the corporate and individual revolution will be driven by an architectural revolution, driven by the shift to digital originals, pictures, and integrated storage, driven by a shift from client-server technologies to distributed technologies that I'm going to describe, driven by a shift from monolithic code to two-tier code to three-tier. This is logical three-tier. It can be in one box, 2 boxes, 5 boxes, 100 boxes, 3 logical tiers in the application. Most important are the core abstractions. What are these core abstractions? So when I think about the 50s and 60s, and I think about the key inventions during that period of time that simplified the programmer's life, that made it possible to build large applications. Despite the massive amount of technology that was invented during that 20-year period of time, I can only think of one core abstraction that fundamentally revolutionized the way that we think about applications. And that was the invention of the high-level programming language. In the 70s and 80s, we had 2 of these core abstractions, databases and user interface. I say graphical user interface, but the fact of the matter is that the challenge of figuring out how to construct a user interface around a 2-dimensional display so that a first-time user can learn to use it quickly and easily, but a power user, somebody who uses it all the time, still is efficient, that challenge that we started facing in the early 70s is still the exact same challenge we face today as we enter the next millennium. So what new abstractions will we require in order to build distributed applications, 3-tier applications that fulfill the architectural change that allow us to change computers so much in the next 10 years? I claim there are 2 of those. Cooperating components, which I'll be describing, and declarative development. Now, another way to think about this is, let's say you're a developer. You've listened to everything I've just said, and you say to yourself, okay, fine, I want to build an application that embodies all these new characteristics. So I'm going to make it 3-tier. That part's the easy part, understanding that there are these 3 tiers as I've illustrated here. Then you face a series of apparently impossible challenges. Do I build my user interface out of pages or out of code? In the business process layer, do I use an object environment that gives me programmer productivity and component reuse, or a TP monitor that gives me transactions and robustness and scalability? And in the storage tier, do I use files or databases? What about when it comes time to connect the tiers? Do I make my application run well in a connected environment or a mobile environment? Do I build the server infrastructure so that it's centralized and easy to manage, or distributed with the advantages that that brings? And finally, what about scaling? Do I use a single large machine or many small machines, and how do I administer it? So last year we actually announced the concept of the Windows Distributed Internet Application Architecture. This year, I want to take the next step in terms of being precise about what WinDNA means. WinDNA is built on top of Win32. Win32 is the Microsoft application platform or operating system platform API set. The good news is that it's powerful and complete. The bad news is that it's powerful and complete. Win32 today consists of about 8,500 APIs and growing. Now, in one way, it's a good thing that Win32 is as powerful and complete as it is. Win32 is what allows Oracle to write a database that they can claim is as fast and scalable as SQL Server. In fact, they'd claim it's faster and more scalable on our own platform. Win32 is what allows Adobe to write Photoshop. Win32 is what we use to write Microsoft Office, IIS, and the rest of our platform and application suite. So the fact that Win32 has to be powerful and complete to allow systems programmers to write highly complex software like that is not surprising, and the fact that we have been willing over the years to make all of our operating system facilities from beginning to end available in a public API called Win32 is one of the reasons that our platform has been so successful. But it's a real problem for business programmers. And so what Windows DNA is a set of 3 high-level services: Forms Plus, Com Plus, and Storage Plus, that are highly declarative and map onto the underlying services. And so it is through these 3 high-level services that we plan to make the platform useful, approachable, and powerful while incorporating new functionality. I want to focus on the user interface layer. Now, the challenge in the user interface layer has been, from my perspective, do you write pages or do you write code? Now, another way of putting this is if you're going to write code, where do you put it? Historically, in the PC industry, there was only one answer. If you were building a PC application or a game, you wrote all the code on the personal computer. And because you did that, you got lots of speed and you were able to take full advantage of the graphics capability of the machine. You ended up with a very rich interface that it could only run on a local machine and only on the Windows platform. Recently, people have become very excited about a next generation of applications written using HTML where all the code runs on a server. And the really exciting thing about these applications, what I refer to as the revenge of the mainframe, is that the Internet, with its distributed name service, allows anybody anywhere to connect to those applications any time of the night or day. Now, I could leave the question there, but there's more to it than just applications that run on the server versus just applications that run on the personal computer. For example, one of the fastest growing segments in the packaged software industry is the Salesforce automation segment, in which salespeople and executives from companies can visit customers, and on their notebook computer they have a database. They also have an application and a variety of decision support tools. They can do territory analysis while they're sitting on the plane. Let's say they're visiting a retail customer and it's a supermarket and they want to show them different ways of putting products on the shelves, what's called facings. They can have a graphical tool to help them do that. They can sit down with the customer and analyze his order history. Or to take a different example, an insurance agent can help you go through projections of what your net worth might look like in the face of various circumstances. And all of this requires code on the server and code on the notebook. It requires us to take full advantage of rich graphic interface, and it's another choice that we need to be able to make. Now, even if we're building fairly simple OLTP applications, now let's say, for example, we're building an OLTP application and we know it has to go out to the world. So a year ago, Microsoft might have said, use DHTML always. And what I'm saying is DHTML is incredibly important, but there are some times when reach is even more important than richness. But there are other times when I want the simplicity of deployment that the Internet gives me. I don't want to have any code permanently installed on the workstation, but I still want more control over the screen, more richness than I can get from simple HTML. I don't want to be repainting the screen all the time. I want to be able to do a little bit of data validation on the workstation. And that's where DHTML comes into the picture. It allows me to build intranet corporate applications because I have more control over the system if it's my own network, and to take advantage of that little bit of extra security. Now, for me, the most interesting category is what I call cooperative commerce. It's kind of a takeoff on e-commerce. And that's, for example, when I'm running Money or Quicken. And behind the scenes, Quicken connects to my banking server, And when I start going into the system and looking at bank balances, they're always up to date. And there again, we have code running in the workstation, projecting a fairly rich graphical interface, but I also have sophisticated code running on the bank's computer, and we have components cooperating with each other in real time. The question you need to ask yourself is, if I'm planning for the future, not around any particular application, but around a class of applications, which of these scenarios can I afford to ignore? We think the answer is none of them. And that's why Forms Plus consists of a layered architecture. At the top of the architecture is HTML. HTML, we are committed to full support of not just the HTML standard, but all the little idiosyncrasies that have grown up because of the incredibly widespread adoption of HTML on the World Wide Web. Beyond that, DHTML gives you the benefit, the ability to control what's going on the screen dynamically. For mobile applications, and it might be kind of surprising for you to see me put this in here, we have the Microsoft Office. So for example, the next release of Office will see Access for the first time really talking to SQL Server in a rich and complete way. The SQL Server that we're about to ship in a few weeks runs on Win98 and on Win95. For the first time, this means that I can construct an application with code on the server and code on the client, and the code on the client can really take advantage of all the personal productivity tools that salesmen and knowledge workers have gotten used to, while also being connected to the code on the server. Of course, when it comes to constructing the more powerful parts of that application, VB continues to play the role that it has for a long time, the role that it's had since it revolutionized the concept of how we construct user interfaces. For really high-performance applications that need more direct access to user and GDI, you have two choices. Use user and GDI directly through MFC using C++, or the new Windows Foundation classes, which today are only available in the J++ environment, but which in the future will be available in other languages, that give you a next-generation class hierarchy that simplifies the process of working with user and GDI. Now, people often ask me, how do I build my application? And I know they're looking for a single answer. My answer is, it depends. Depends on what you want to do. But what about across all my applications? And the answer still is, it depends on what you want to do. Now, if the question is which architecture should I pick, then I do have a single answer. The key difference between the Microsoft Forms Plus architecture, because that's what Forms Plus is, a framework, an architecture, is that our architecture is designed from the ground up to offer you a choice, to offer you a smooth continuum between power and richness versus reach, so that it's not a versus. And that's a choice that I believe you should look for, not only in terms of the applications you construct, but in terms of the ones that you purchase as well. So I'm going to be building up a diagram that shows all the pieces of WinDNA, and what I've talked about so far are these pieces that you see in the architecture diagram. Okay, so now I want to talk about the middle tier. The key challenge with the middle tier is it's easy to explain, at least it is these days, why you want to separate the storage layer from the business process layer from the user interface layer. The challenge comes in when you start trying to figure out, how do I write all that business logic code? Now, I've been saying this for a long time, and it's still true, that when you go out and look at client-server applications, or people who are trying to write three-tier applications, more often than not, what I find is that they end up making one of two choices. One choice is putting a lot of code in the client. The other choice is putting all the code in the server, and quite often when it comes to OLTP-style applications, a lot of it ends up being database triggers or stored procedures. And why is that? A lot of the time these days I also find that a huge amount of the code ends up being scripts inside the web server environment. Now to me, the common element between database triggers and stored procedures versus, say, ISAPI scripts is the idea that we can't use a full-power programming environment. We can't use the programming languages that have been developed over the years and the debugging tools. We can't use the globally optimizing compilers and all of the rest of the runtime environment. And why is that? The reason is that when you look at the challenges of creating web-based components, the infrastructure to make that straightforward and easy until recently just hasn't been there. For example, if you look at RPC, the client side of RPC is dead easy. The server side of RPC is beyond the ability of most programmers to write, which is one of the reasons that if you look inside, let's say, the SAP R3 system at the high end, or the ProLogic banking system at the low end. So on the one hand, you have a company with thousands of developers, and on the other hand, you have a company with less than 100 developers, and you find that both companies ended up having to write their own TP monitor. Because when it came to dealing with issues like memory management, request handling, thread pooling, connection management, data binding, security, error management, and faults, that's too much work for most programmers to do. So it's about 2 years ago now that we introduced MTS, Microsoft Transaction Server. If we were introducing the product today, we would call it Microsoft Application Server, because as it turns out, we helped to define a category that's come to have that name. My goal when I chartered the MTS team was threefold. The first was to write what I thought of as a TP monitor, something that would simplify the development of middle-tier applications while providing robustness, scalability, and security. My second goal was to simplify the process of developing those kinds of applications. The story that I have told in the past, which is still true, is that my challenge to the team was that most developers should be able to learn to use MTS working off only the liner notes inside the CD-ROM that it shipped in. Since then, we've realized that the right thing to do is to combine MTS with COM and to produce a next-generation technology that we call COM+. Now, COM+ sits on the Beta 2 disk of NT2 in the preview section, and will sit in with the rest of the NT code in Beta 3. COM+ first chips as a production technology with NT5. So what COM+ does for the first time is it makes it possible to write a middle-tier application, to write middle-tier components as simply as writing VB code, packaging it up as a DLL, and then marking it as a COM+ component. But the challenge doesn't stop when you've made it possible for a workstation or a web browser to communicate with a single server. What about the challenge of allowing many servers to all communicate with each other? That's where the power of the declarative environment really comes in. Now, I found in talking to people about distributed systems that there are generally two theories about distributed systems. The first theory is that they're really not possible. You can talk about them, but you can't really build them. Of course, if you carry a credit card, you know that distributed systems work because you can fly to any country in the world, including third world countries, go into a store, hand them your credit card, they'll swipe it through the Verifone reader, and within a minute or so, you'll know whether or not you've exceeded your credit limit. So somehow a distributed system is working. It works every day with bank ATMs, works every day with airline reservation systems. The second theory about distributed systems, which is true, is that traditionally they've been far too hard for ordinary people to build. So there are more myths. For example, another myth is about two-phase commit, the core technology that most people assume lies underneath any distributed system. So on the one hand, most people think that you can't build a distributed system without only using two-phase commit. And yet on the other hand, everybody knows that if the entire system is linked together by two-phase commits, that somehow, whenever any line or any server goes down, the entire system grinds to a halt. Now there's something wrong with the model that says that having many computers is more fragile and more unable to resist faults than having a single large computer. The core of the problem is that the amount of technology required to really build the distributed system is staggering. You need RPC, you need two-phase commit, you need message-oriented middleware, you need objects, you need transactions, and these days you need the web. And it turns out that the challenge of finding a programmer who can deal with all those different technologies all at the same time, all in a single application, is overwhelming. So that's one major problem. The other major problem is how we conceptualize the challenge of managing a distributed system. So for a long time, when people think distributed systems, they tend to think client-server. Even today in the days of the web, even though it's kind of a passé term, once you get past the browser, when people think distributed systems, they think of a client, which today might be a terminal, a browser-based workstation, or it could be a rich workstation, and then they think of servers as though there's only one type of server. So if you think client-server and you ask yourself, where does the management of the distributed network take place? It's not on the desktop, it must be in the server. And since the server is a database, people end up believing that distributed systems are about distributed database. Microsoft doesn't believe that distributed database works. That doesn't mean we're not investing in distributed database technology. The replication and transaction coordination technology that we've been shipping for a number of years and that gets better with every new release, I believe defines the state of the art in terms of distributed databases. What we believe, though, is that the key to a distributed system is not in the database layer. That in order to reach the promised land of distributed systems, you have to start with the concept of three-tier application architectures. And then once you have three tiers, when you ask yourself, where should the distributed system be managed? Now instead of two choices, there are three. And the answer is not the database tier or the UI tier, it's the middle tier, the process tier. So there are two innovations in COM+, even in COM+ 1.0, that for the first time make it possible to really build distributed systems in a fairly straightforward fashion. The first is that COM+ 1.0 unifies under the single concept of a method invocation a variety of different ways of communicating, from real-time communication between servers when the line is up, with two-phase commit being done transparently and under the covers automatically, or switching transparently and automatically to queued communication when the line is down. That's the first key concept. The second key concept, which is as much a part of the declarative model as the first one, has to do with transaction propagation. And what this second key example illustrates is why a declarative environment is not just a really nice thing to have, a great way to simplify the programmer's problem, a nice way to make complexity go away and make things become useful. It turns out that a declarative environment is actually necessary. It's absolutely essential to make distributed systems really happen. So let's take this example that I have on the slide. A user queues up a transaction or makes a transaction request, which goes to an initial process that makes a request against the database server. That happens in the context of a transaction. That first process, I'll call it A, makes a request of an intermediate component sitting in the middle of the middle tier that I'll call B. Now it turns out that that middle component, which happens to do sales tax computation, doesn't use any databases or files. Itself, it's not transactional. Component B, in turn, makes a request of component C, which works with both a file and a database. Now here's the question. So now let's say C, which is doing a transaction, wraps up its transaction, returns control to B, B returns control to A. How do I get the entire thing to happen as a single transaction? A and C don't even know about each other. They might be using different databases. There's also the file system in the picture, which certainly doesn't know about the databases. The answer is that COM+ knows. When A makes a request to B, the transaction context is propagated transparently and automatically. When B, even though it itself is not transactional, passes the request on to C, the transaction is propagated again. Even more interesting, it's not just propagated across three components. When B goes to close the transaction, when C does a transaction commit, COM+ invisibly converts that transaction commit to a transaction prepare to commit. So now the databases have been involved, even though they don't know about each other, have been involved in the fact that this is a distributed transaction. And when A finally comes to commit the transaction with its database, COM+, again, transparently and automatically, declaratively, so to speak, goes through the two-phase commit voting procedure and causes the entire distributed transaction to either complete as a whole or be rolled back as a whole. And without the concept of this kind of declarative cooperation, this kind of distributed system would literally be impossible to build. So now we see more of the pieces start to come together. We see Forms Plus and COM Plus. We start to see the distributed transaction coordinator and the transaction propagation mechanism. We see the connection between the transaction coordinator and the underlying record store, which allows us to convert a transaction commit to a transaction prepare to commit. This starts to look like a real architecture. Still not enough to do distributed. The definition of distributed became at least twice as complicated with the introduction of the Internet. For the simple reason that, and particularly also with the introduction of notebook computers. It used to be that when I said distributed, you immediately thought server to server. That's still distributed. Now you also have to think notebook to server, to server to server, and back to other notebooks and desktops. Not only that, but it turns out that even what it is that we're coordinating is more complicated than most people assume. If you talk to the component people, they'll tell you that distributed is about methods and about remote procedure calls and function shipping. If you talk to the system management community, they'll tell you that distributed is about events and propagating events through the network. The database community, of course, will tell you that distributed is about distributed database and propagating data and changes to the data through the network. And I'm telling you it's about all three. So a year ago, I started talking about the fact that just as interesting as the idea of moving the client to the server is the idea of moving the server to the client. And a year later, I'm in a position to say that we've made enormous progress towards achieving that goal. So, for example, when I talk about SQL Server 7 being available on a Win95 or a Win98 machine, part of that is a challenge of making it just run on another operating system. Part of that challenge is making it have a small working set. Now, most of you probably assume that, oh yeah, I can run SQL Server on my notebook as long as it has a gigabyte of memory. Well, if you want to support 500 or 1,000 users off your notebook, you probably need a gigabyte of memory. But if you want to support yourself, a 2 megabyte working set or a 3 megabyte working set is more than enough. In fact, SQL Server 7 at the time it ships will have about the same working set requirements for a single user that JetRed does, the engine that's inside Access today. So working set is part of the issue. The biggest part of the issue, though, with all of these pieces is understanding that anything that runs on a notebook has to be a V3 product. For example, we went out and interviewed users of one of the leading small business accounting packages about 2 years ago and found out that 80% of those small business users turned off their transaction log. Now, I've never met anybody who says to me, I want to lose data. I want to lose transactions. You know, it's up there in the category with hit me or kick me. But it turns out the reason they turned off the transaction log is they didn't want to administer the transaction log. They didn't understand the questions they were being asked, and even when they did, they didn't want to deal with them. So SQL Server 7 has a transaction log, but in the case of the notebook version, the transaction log is self-running in the same way that the database is self-growing and self-shrinking. Even in large environments, one of the amazing things about SQL Server is that the queries in the product are self-optimizing, something that nobody has ever done in the database industry before. People have tried, but they've never succeeded. We found during our beta testing that users will call us up and complain about performance problems, and by the time we call them back and they say, oh yeah, we don't quite know how the database did it, but it not only fixed the performance problem, but then it continued fixing it, and now we have better performance than we ever even thought was possible. All of that is part of being a V3 product, and all of that is part of client-server symmetry. All of that is part of being truly distributed. It also means having a common framework for all of this to work. So it means the idea that from COM+, even events end up moving through the same method invocation architecture that I described earlier. To us, an event is an unbound method invocation. So what does that mean? Let's say that I have an application that might run out of disk space, and I want to be able to notify people when I've run out of disk space. So I create a subroutine call, to use the old-fashioned word, called ran out of disk space. Now normally if I said call run out of disk space, and maybe there's some arguments that I use for passing data, somebody has to be at the other end to receive my method call. But if I declare that ran out of disk space is an event, the compiler and the link editor, to use another old-fashioned word, will allow me to have this dangling method call, because that's what an event is, a dangling method call, and then it will allow somebody else to come in and bind to that method call after the fact. But if an event is a method call, that means it can be queued to real time, it can be transactional, it can benefit from all the same infrastructure we've put into place for events. And that too is all part of making distributed really work. My final example of what's required to make distributed really work is again a replication-based example. If you haven't learned about SQL Server's replication facilities, you need to. Why do you need to? Because it's amazing how many different kinds of replication, including ones you don't normally think of as replication, are required to work in connected and disconnected environments. So for example, one of the types of replication we put into SQL Server is the kind of replication you find in Lotus Notes. It's not transactional, but it operates well in a disconnected environment. So now for the first time, I can have a notebook computer with contact information for customers, make a change, go on a canoe trip, come back 6 weeks later, and it's okay that I was away for 6 weeks. My changes will still go to the server, and I'll get all the changes the server has seen over the last 6 weeks because there's no log that overflows. So now we see some more of the pieces starting to come into play. And what about storage? To me, this is the area where we're going to see the biggest innovation. So let me illustrate some hard problems. Build a sales forecast and include spreadsheet-based sales plans and project-based campaigns. How do I combine data in a query from all those different sources? Back up my mail, my documents, and my databases coherently. Find all the trip reports for staff with expense reports over $5,000 during the last month. Okay, the expense reports are in a database, but the trip reports are Word documents. Who's coming to my 3 o'clock meeting? Show me their most recent mail. on the topic that the meeting is about. Now, we can solve that class of problem by putting some common facilities, some common infrastructure underneath our stores. Again, this is work in progress. For example, if I say OLADB, most of you will immediately think about heterogeneous queries, the ability to do a query that includes spreadsheet-based data, project-based data, data on a web page, and data in a database. It's technology that we've been shipping for a while and that becomes completely mature with SQL Server 7. But when I say OLADB, how many of you also think about transaction coordination? The ability to coordinate transactions across all those different stores so that updates as well as queries can be coordinated as well. Or common indexing. With SQL Server 7, for the first time, you gain the ability to combine content index-based queries with database-based queries. So that all comes from what I call plumbing. So here's the way that I think about this at an even deeper level. If I said to you, any one of you, how much memory do you have? You're all going to give me an answer in megabytes. Okay, now if I say to you, what's your oldest memory? I've tried this experiment about a dozen times now, and as soon as I ask people what their oldest memory is, there's a pause in the conversation. People get introspective. About half the time they answer the question and tell me about something from their childhood. But why shouldn't the computer's memory be an extension of our memory? Now the reason it isn't because it can't store memories. It's because it has no way of organizing them. And in fact, the most embarrassing example of how deficient, how brain dead operating systems are today, because it's the operating system that's at fault, not the disk or the silicon, is that the operating system today, and I'm talking about all operating systems from MVS and DOS 360 through Unix, through OS 400, through NT and Windows 98, have no concept of the world around them, no model. And they don't even have a model of that most basic thing, an application. I mean, if an operating system's reason for being isn't to run applications, I don't know what its reason for being is. And yet the operating system has no notion of what the pieces of an application are or how they fit together. And that's why you can't click on an application and drag it from one machine to another. That's why when you install a new application, you have to worry about breaking old applications. So the answer to this problem is fairly straightforward to say, and we're fairly well on the way towards doing it. It's to build a model of part of the world into the operating system. It's a schema, but a schema with some behavior. So it means having what I call a social model and an operating environment model. The social model is people, places, times, addresses, roles, reporting relationships, so that finally we get to the point where there's a single way of storing a person's name and address, so when you change that name and address, that change shows up everywhere. And the operating environment is what's inside the computer, the structure of an application, what's stored on the disk, what the configuration of the computer is, and so on. So the last section I have in the architecture deals with scaling. I thought about leaving this section out because I was afraid, as I am, that I'd run over time. But I get asked this question so much that I felt it wouldn't be right to talk about WinDNA without talking about will NT ever scale. All this stuff is really cool, but if we don't scale and you're building a big site, what good is it? Of course, if you want the one-word answer to will NT ever scale, the answer is yes, but I'm going to get a little more detailed than that. So I have 4 definitions for scaling, and let me be clear, the reason I have 4 definitions is not to weasel out of the really hard one, but it's to point out that there are some others as well. Classical scaling, that's what people think of as the hard one, where the state of the art for the most part is around 30,000 TPC-C transactions per minute in the database environment. When will Microsoft be number one or at least be close? And the other state of the art is when will I be able to build a 1 terabyte data warehouse with Microsoft SQL Server on NT? But then there's scaling down. I think it's just as important to ask, when will, pick your favorite platform, really scale down to move into V3, as I've already described. Then there's scaling out. Who's working and making distributed finally possible? Now, I've talked about those two. The most interesting to me is real scaling up. And that's the one that's the most interesting to me. Because if you think about the fact that the world has about 6 billion people in it, and then you ask yourself, what percent of that population will one day be using computers in one form or another? Not all day, but some of the time. You can pick whatever percent you'd like. I've never had anybody say 50%, but I've also never had anybody say 1%. Most people pick percents in the 10 to 20% range. That means sometime in the next 10 to 20 years, there will be 500 or 600 million computer users. If you build a popular website, how many users do you need to be able to handle? Now, if you said to me, I want to build a system to handle 100 users, hey, that's easy. Hire a programmer, build the site. 1,000 users. Well, you better be careful. You better interview your programmer carefully. 10,000 users. Now you need a development team, and you might not succeed the first time. You'll probably get there. 100,000 concurrent users. Not 100,000 user population, 100,000 concurrent users. There's probably only 2 or 3 teams in the world who have ever built a system that scales to tens of thousands, let alone 100,000 concurrent users. Your probability today of being able to build a system that could handle 100,000 concurrent users is incredibly close to zero. And yet somehow in the next 10 years, we all need to be able to get to the place where building a system that could handle hundreds of thousands or even millions of concurrent users is at least imaginable and not impossibly difficult to do. And so Microsoft is dead serious about challenge number 1, you bet, but also challenges 2, 3, and 4. So let's talk about TPCC. First thing is, TPCC numbers are improving amazingly fast. You know what? It's not because we all hire good programmers. It's because Intel is getting better and better at converting sand into processing power. All by itself, Moore's law and increases in disk capacity and disk speed would make TPCC improve by itself, even if database technology and transaction processing technology hardly improved at all. And we're all getting better at making our software run faster. So that's the first thing to note. Microsoft still has a challenge ahead of it. Now let's be clear. Microsoft has no problem with things that take a long time. Anybody who used Windows 1.0 and Windows 2.0 or Word 1, 2, 3, and 4 know that. So we really became serious about entering the database industry about 5 years ago. If you go back to the time when we first got into the server operating system and database industry, that goes back 10 years, hardly a long time, considering how long mainframes and mini computers have been around. If you draw the graph, it will become clear to you as you look at the progression that Microsoft is on a path to having TPCC numbers that are state-of-the-art, as good as anybody else's, and the only question is when our line intersects their line. And I'm not going to predict a year. I think it's within the next 4 or 5 years. Could be a little sooner, could be a little later. It's going to happen. To me, it's a certainty, and the only question is when. But it goes beyond that. Why don't most people drive trucks? After all, trucks have more horsepower and more carrying capacity than cars do. Or why doesn't everybody buy the fastest sports car they could buy? In fact, you really don't want a sports car, you want a motorcycle, because nothing accelerates as fast as a motorcycle. So the real question isn't how big or how fast. The real question is how big and how fast is big enough and fast enough. We think, for example, that when NT5 and SQL Server 7 are both shipping, that if you're running a Bond or an SAP or a PeopleSoft system, if you were to go out and look at their entire installed user base, you would find probably less than 1 or 2 dozen users worldwide who couldn't very comfortably run their system with a substantial amount of headroom with the hardware-software combination that will be available then in the Microsoft environment. And if that's not quite good enough for that 1 or 2 dozen, if they simply wait a year, things will take care of themselves. So are we committed to getting better? You bet. Are we now at the point where what we have is good enough? We think it's more than good enough. And then there's the question of how much you're willing to spend. So what about the millions of users? So there are 2 big things that are changing in that environment. One is commodity clusters, and the other is huge amounts of memory. What happens when you can buy the amount of memory required to keep your entire 50 gigabyte database in memory on a credit card? Memory access is around 7 million times faster than disk access. And so with COM Plus 1.0, we are shipping the world's first high-volume commercial in-memory database. A coherent cache that allows you to populate the database from an underlying SQL server and propagates updates and transactions transparently back to the SQL server for you. The other piece of the puzzle, though, is commodity clusters. This is an example that I showed last year of a cluster we built in the labs designed to process 1 billion transactions per day. Built entirely out of off-the-rack computers. The cluster at the time we built it, retail price was worth $2.5 million. Today you could build the same cluster for $1.2 million. And finally, in terms of that terabyte warehouse, we think when SQL Server 7 ships, we'll be there. In fact, we are running today a site on the internet which you're welcome to go to called the TerraServer, which we believe is the largest database on the web. 1.3 terabytes of data. We've had 99.95% uptime since June 1. No downtime, period. 24 hours a day, 7 days a week, the entire month of August or the entire month of September. So now you see the complete picture coming together. Anybody setting out to build next-generation systems really does have a serious dilemma. And we view it as our job to understand the challenges the developer faces and to make computers useful, to make them approachable for him and exciting for the users of his applications. We announced the WinDNA architecture about a year ago, and at the time, not very much of it was actually shipping, but we were able to describe the rest. This year, we're able to describe the architecture in more detail, and quite a lot of the rest of the architecture is now either shipping or in late beta stage on the verge of shipping. So we still have work left to do to make the architecture complete, but as you can see, more than half of the architecture, depending on how you measure it, is already real today. What I'd ask you to remember when you think about this presentation is how different the world will be and how we're going to work together to make computers useful in that different world as it starts to emerge. That's what we're setting out to do with WinDNA, and that's what we hope you'll do with the applications that you build above it. Thank you very much.